Hello, hello. I don't know if you didn't see I have the same slide as the first slide as I did last time. I usually travel incognito, so no one can recognize me. Those are all me. You may have seen me in a different form. As Laurie said, I'm the founder and CEO of Circonus. Circonus is a monitoring company. We're a diamond sponsor here as well, and that should probably be the last thing you hear about Circonus. Even though this is about monitoring, this is really about design principles of monitoring and what you should expect out of your monitoring system and how you should be thinking about monitoring. And it really doesn't have many references to specific products or tools. There are specific technique references, but we'll leave it at that. There are some rules in there that may come out as you're doing it wrong. Don't take them personally, just go fix it. There are some bad design patterns in existing monitoring solutions. My marketing would hate me saying this, but we have some anti-patterns in our product. If you look at like Nagios or Sensu or Graphite, Grafana, Prometheus, a lot of these have some really horrifically bad design patterns that are like 5% of the implementation. The other 95% is really well aligned. You didn't marry your monitoring product, so you don't have to accept all its flaws. You can just move on and do better. So this is kind of broken up into three parts. The first part is an overview and a history of how monitoring came around and what we used to do and what we kind of do now and where we might be going with that. The next part is talking about service level objectives, which are critically important to the mission of SRE. And then we're going to drop back into some simplistic design and monitoring tenets, things that are truths that you must come around to eventually. So it's kind of funny. We run a monitoring as a service company, and it's kind of like of all the bad decisions that people make and you reflect on them, right? It's like I started a company to draw graphs of outages so that any outage we have is permanently memorialized in everyone's graphs, right? So it's like, well, that was really poorly thought out. So we're doing fine, but when you think about it, it's like, well, I really took a stupid risk there. That was not smart. What is monitoring? So this is, I won't say strongly debated, but I think it's important to understand what our goals are. So monitoring is the action of observing, checking static and dynamic properties of a system. It's pretty simple, right? The problem is what the hell does the word checking mean? That's a really complicated thing. I think observing is pretty obvious, right? You just want to understand how a system is behaving. So I focus a lot on systems behavior. So one of the things that's really important to remember about monitoring, and I think SREs kind of have an edge up over most other computing disciplines, mainly because their purview is pretty wide. It's both in writing code and deploying it, operating it, making sure that it's accessible to users. So you see a little bit more of the life cycle. But it's really important that your systems are not your computers. They're not only that. They are a lot of other things. And they include HR and finance and sales and marketing and all the other aspects of your organization. So if you do not have sales and marketing, it's very unlikely you will have a job tomorrow to build a product because no one's buying it. So it's very important that the entire delivery pipeline of the product, not just delivering service, but delivering sales of the product to service customers, is also part of the system that you want to monitor. It all has to behave correctly. And the goal of monitoring in a lot of ways, there's a lot of talk of like using ML and AI and doing anomaly detection and having it all be magic. The interesting part is that everybody's systems behave a little bit differently than everybody else's systems because you write custom code and that code executes in different ways than my custom code. So what you're really looking for is changes in behavior. and you're trying to correlate those with changes in circumstance, either things that you caused as a human, like deploying code or writing code, or situations like an availability zone in Amazon failing, or a network cut, or something like that. So you're trying to correlate outside influence and systems behavior. So let's look at web monitoring, which is something that we kind of all take for granted today because I think it's the furthest evolved. There's a lot of money behind it, so it's really important. When we look at web monitoring in 1995, anybody here operate a website in 1995 or something? Yeah, it's a good number of hands, okay. It was awesome, right? Like when Keynote and Gomez first came out, they would load your website every 15 minutes and be like, it worked. And you were like, oh my God, all of my bases are covered. This is so fantastic. I have complete awareness of the availability of my system from everywhere in the world. And when you think about it, it's a valuable service. It's great. And when you look at what we have today compared to that, it's like, that is kind of a tragic oversight and inconfidence. So one, no transaction Keynote or any of these synthetic monitors did ever improved your business. They didn't actually buy anything off of your website. They weren't a user. Not only that, they were everywhere in the world your users weren't. They were in data centers. So it's like, oh, users from France. It's like, no. The data center in France can get to you, not the person on some rue somewhere, right? You didn't have good visibility into what was actually happening. So it was really obvious with JavaScript when that came out, you could embed analytics into web pages that you could track users. And I am not going to get into the legal aspects of any of that. I'm going to go into the technical aspects of the challenges of that. But the data volume for that was really big at the time, right? So every single web page that someone comes and loads, you want to track how they interact with the site, what web page they loaded, where they came from, what their IP address was. Like all of the various different performance timings as those started to come out, DNS resolution time, redirection times, all of those things. And basically you got a view of what was actually happening on the site. So you have synthetic monitoring to make sure that your site could work. And then you have real user monitoring, which was RUM, which everybody's familiar with RUM probably. That came out, and we now actually saw what was happening in the system. We could actually see real users using the site and having a bad time, having a slow time, and we could surgically improve those things. So we were able to set our service level objectives around actual user experience. And this changed everything, right? So does anybody not use RUM? Okay, good, because if you raise your hand, you might get laughed at. But like if you turn on Google Analytics, you get all of this, right? And almost every service that's out there that does web monitoring does this. And what we got in 2015, I think, was really the ability to store every single interaction ever on every dimension and be able to query that. So if it's important enough to your business, you're willing to pay the amount that it takes to get something comprehensive, and you can slice and dice in every possible way. And the reason this happened so early on is because this is not big data. This is tiny. How many users do you have? 100 million? Billion? 5 billion? How often do they click? Once a minute? They don't. But if they did, it's like, okay, so now I have 5 billion measurements a minute. That's not big. It was in 1995. It was enormous. We didn't have systems that big. But when you think about why this data isn't really that big, it's because users are slow, right? Computers are fast. Users are slow. So we had this evolution, and we had all these awesome things in the web, but we wanted them for other things. So guess what else is really slow compared to computers? Computers doing complex work like databases. So databases were a great first target. When you look at a database, there aren't too many databases out there that do more than like 10,000 or 100,000 transactions a second, right? So when I talk about speed, we're talking about how many people have a 32 core box? It's pretty common. Each of those cores runs at 2.5 ticks per nanosecond that are doing instructions. So if you're going to count things like, I just had an instruction cache miss or a branch misprediction on my system, and I want to track how many nanoseconds of latency or how many clock ticks that introduced into my program, I want to track all of those. Now you're actually working at the speed of the system that would store the data to analyze the system. Right, so that's where the kind of inception problem happens. But in databases are kind of relatively slow relative to computers. So we had the same sort of thing. In 1995, we would log into the database and run a query, and it would come back and be like, oh, it's fast, everything's wonderful. But what turns out is that it was something very different happened. If you have users just running queries on your database, you probably have all sorts of security problems. But in 2005, we have all these developers dynamically creating workloads on our systems and launching code every 5-6 hours into production that changes the behavior of the system. So now we do actually have users. They're not customers, they're customers, right? They're internal customers, right? The customers of the database are the developers. So what we had was this same sort of problem where I need real user monitoring of my database. I want to see every single query that's run. I actually want to see every single file system buffer cache block that's evicted due to a query running. I want to see every table that's scanned. I want to know how many tuples come back. I want all of this information. It's right there. Why can't I have that? And the answer was, well, that's one, it's hard to get. There are a couple of databases that introduced that, and then it was hard to collect. Then we collected it was hard to store, then we stored it was hard to analyze in real time, and then we sort of figured that out. And by 2015, we now have real-time analysis systems for like every query that can run through a database. You can buy tools today, turn them on against your database, and watch everything that happens. You know the nanoseconds of latency of every single query. You can get new query profiles. All of those things are visible now. We have observability in the right place, and we have the technology to start powering that. So then we have the latest, most latent curve in this, which is the idea of real systems monitoring. And this one is the hardest one of these things because now we're actually trying to monitor systems at their most accelerated state, right? So I've got a data center of computers and I want to look at systems. I want to understand the behavior of systems. When I say that, what is that? That's the latency of CPU cross calls. That's the latency of syscalls that are happening, the cost of a page fault, all of those, right? Now you're talking about things that happen millions and millions of times per second on each CPU, on each server. I want to track the I/O latency of every IOP. If you're running a server full of NVMe cards, you're talking about a 500,000 IOPS a second on a big box. I want the latency of every single one of those IOPS. And the reason is, people are like, well, I don't need that. It's like, well, in 1995, nobody needed to know every user's behavior. Turns out no one can live without every user's behavior now, right? The only reason people don't need it is because they don't know how to do it. That's where we're going. We're going in a place where that is now starting to be table stakes. So if anybody went to the Linux performance workshop, I think eBPF has been mentioned in a couple of different talks. eBPF is the subsystem inside Linux that was recently introduced in the 4 series that allows you to instrument arbitrary parts of user space and kernel. So you can actually arbitrarily check the latency of every single system call that happens. You can pull that out. You can start to create and store information around that. So again, we have to make some compromises there, but this is what's coming. The idea of like pinging my box and seeing if it's up, it's kind of sailed. That ship has sailed. That is not the, oh, we're good, everything is pinging. We actually expect our systems to behave well and deliver good service. So it's important that we start looking at the entire system's behavior. So monitoring has become very sophisticated out of the whole, I ping my box, everything's happy, I can go home at night and sleep well. So the increases in telemetry volume, so all of these measurements that are coming in, I mean, if you think about having 1 billion measurements in 1 second coming off of one box, that is something that we can do today. So the question is whether or not we can leverage it for value. I think the answer is yes. Time series databases have made some leaps and bounds in their abilities to handle this sort of volume. So that's really awesome. And streaming analytics systems have really changed over the last 5 years. So all these, there's like 1 million products now that have popped up, but like things like Apache Spark and all these other stream processing systems that allow you to apply complex analytical processes to real-time telemetry flow. It means that everything can shoot across the wire at millions or billions a second, and you can make interesting insights now about that data, within a couple of milliseconds. So I think the second thing is that because of this influx of data and because of advances in data science on that, what we're seeing is that people are asking really, really good operational questions now. They're asking capacity planning questions about everything in their architecture because it's easy, right? You're looking at disk space usage. It used to be, when you operated databases, every week or every 2 weeks, you would take a chart of the disk space usage over the last month, and you'd plug it into Excel, and you would run a linear regression on it, and you would try to figure out when you were going to run out of space. Right? It turns out that that's highly automatable, right? So now the idea that I have any sort of resource curve, I can just get that information immediately as like an overlay. Right? So I'm looking at a graph, and it's like, hey, by the way, that's going to hit 0 in 7 days, 3 hours, and 12 minutes. Right? Like that sort of math is easy. So what we're starting to see is that sort of analytical power applied to all of this data and being surfaced for operators. So that's interesting. And then the third thing that really dramatically changed the way monitoring worked and our expectations of it is that organizations, they move damn fast compared to the way they used to. So it used to be that we observe the behavior of the system, and you're like, well, what are you looking for? Looking for changes in behavior. And every 6 months or 9 months, someone would do a product release, and you would obviously see a lot of change in behavior, and you would reset your baselines, and you would figure it out. Okay, so now you ask a development organization what they're supposed to do, and they're like, I'm supposed to change behavior every 6 hours. Well, that makes it really hard to use tools to detect behavior change when the goal of the development organization is actually change behavior to the system. Right? So they're constantly launching new code, and because the architecture and the models change so fast, it's very difficult for monitoring systems to apply a lot of the traditional techniques because your baselines end up changing so often. So we got a lot of challenges. So the way that we cope with this, in a lot of ways, is by identifying discrete and simple, easy to understand service level objectives. So I'm gonna hopefully leave you not too confused and depressed by SLOs, but almost every SLO I have ever seen in my life is written in a way that it cannot be assessed and is almost worthless. So here's a great example of an SLO that I've seen before. 95th percentile should be less than 10 milliseconds. I've seen this, 99th percentile, everybody knows what a 99th percentile is. If I have 1 million samples, I sort all of them, and I choose 95% of the way down that sorted list, and that's my 95th percentile. You can do a little bit of math if it doesn't fall on an exact number, but with a big sample set, you're fine. So basically, it's the 95th percent slowest transaction that happens, or whatever you're measuring. Okay, so one, it's not simple. 95th percent is not simple to calculate. So what that actually means is that we don't have a set of time here. Is that 95% of what? Of samples, right, of latency measurements. Say I am servicing a API service. So there's an API service where someone needs to check authentication information. So when that API request is called, it's a REST call or gRPC call or whatever, that thing should be fast. 95% of the time, it should be faster than 10 milliseconds. Okay, so that's a typo in the slide, that's not 1%. 5% of them, what that also means is that 5% of them can be arbitrarily bad and everything's great. Right? So if I have 100 samples, 5 of them, 101 samples, 5 of them could be 10 minutes, and everything's good. We've met our SLA. Okay, that's pretty crappy. That's not a good idea. The other thing is that we haven't set the time frame over which we calculate the percentile. Right? So it's 95% of the samples. The samples since you were born, the samples since the service booted, the samples for the last 5 minutes, for the last day, for the last quarter, over what time period? And without that time period, there's no way to really hit this objective in a positive way. You're always gonna figure out a way that you failed, and it's really bad. So typically what I see, the easiest way to qualify that is say, okay, let's just pick an arbitrarily small time quantum, like a minute or 5 minutes. And what we'll do is we'll split every day into 288 5-minute chunks, and we'll calculate the 95th percentile inside that 5 minutes. And if I'm good, I'm good. If I'm bad, only that 5 minutes was in violation. So that's one way to describe an SLO that can actually be assessed. Now remember that if you want an SLA around your objectives, and you say, I shouldn't violate my SLA more than 0.1% of the time. So I should have 99.9% of the time I am in compliance with my objective. If you measure 5-minute chunks, you burn those up real fast. Right? 5 minutes is a long time. So there's a lot of thought that needs to go into how you calculate these things. It's also not really simple if you're using any of the common open source SDKs. Some of them are right, but most of them are not right. When you put samples into something using like a replacement algorithm and you get an approximate percentile out, it's not actually the right percentile. It's the wrong number. So now you're using tools that aren't adequate to feed numbers into a system that you're held accountable for. It's pretty stupid. You shouldn't do that. So there are other questions about this, right? Even once you've articulated and say, okay, we're gonna do it over 5 minutes, we'll do it over 1 minute windows, and we'll calculate 95th percentile over those 1 minute windows, and we'll make sure that the 95th percentile is faster than 10 milliseconds. Why? Why is it 95%? Why is it not 95.1? Seems close. They both can't be right. Like, that number is really arbitrary. 10 milliseconds? Also really arbitrary. So you've gone through great extents to describe an SLO in very crystal clear terms with arbitrary parameters. Keep that in mind. And the real tragedy of all this is that the classic techniques, the ones that are promoted most in the industry, are not using distributions of data to calculate the percentiles. They are using either fixed space replacement algorithms, or they're doing it over rolling sample sets, which don't give you the same answers. So you can't say, oh, what's my 95th percentile over an hour as opposed to a minute? And it's like, oh, we'll just average them together. Well, the average of a percentile is go screw yourself. That's not anything. It's useless. It can be incredibly misleading as well. So in order to actually calculate accurate percentiles, you either need to store all of the samples or you need to store a complete distribution of the samples. So you need like a probability density function style or cumulative density function over all of the samples. So you need that as well. Easiest way to do that in low volume systems is just store all the samples. You can go back and reference them later. Because the real problem is when you want to change one of those numbers, like 95 or 10 milliseconds, you can't go back. If you've only been storing percentiles, you can't go back and say, well, what if we do 97th percentile? That's better. Let's up the ante and do 99th percentile. 99% of my queries should be faster than 10 milliseconds. Did we meet that over the last month? I don't know. We weren't collecting that. Okay, that's a bad answer. So I'm going to give an example through graphs. So this is 5 weeks of data of database queries. And because I had problems with my memory, I intended to do an average here, but I did a median. They actually end up being fairly close. But this is a median. That dark green line is a median latency of database queries. And they happen to be a median around 400 microseconds, which is great. It seems awesome. This is a 10 millisecond goal, right? So we're doing 10 millisecond goals. Our median is there. This is the actual distribution of all of that data over 5 weeks. It's 36 million data points that go into that histogram. And we can see that we have a really strong spike around 200 mics. Our average, as we saw, our median, was around 400 mics. There's other things that are really interesting that you don't see if you just look at an average or a median. You actually see modality here, right? So I can see that there's pretty clearly 5 separate modes of latency. I have 5 different workloads in there, at least. So the interesting part is, what does that look like over time? So this is a technique called heat maps. There are 2 types of heat maps. One is where people click. That's not this kind. This is a time series histogram view. So every vertical bar in here, the darker the color, the more samples in that bin. So the bins now go on the y-axis, not the x-axis, and time goes on the x-axis. So if I look at this, I can see in this area, this is visually anomalous. I can look at this and say, hey, I have more samples right there in those circles than I do to the left or the right, so clearly my workload changed. And if I look at them, if I put like a hairline over that, I could see the actual distribution at that point in time, which is pretty different than if I highlight one of those nasty ones that has a huge second mode that's out there. And this is the type of information that you need to know to actually understand the behavior. If you're looking at the average or the min and the max, you're distilling 36 million samples to 3. Not very illustrative of the actual data set. So it's really critically important to actually track all this information to build a good picture of the behavior of your systems. Otherwise, you can't see these sorts of modes emerge and you can't align them with other things. And the reason to keep them in time series, of course, because the whole world works on clocks, is that you have developers releasing code, you have marketing doing a launch. So being able to correlate all of these external factors into, oh, I did have a behavior change, leads you to the one thing that computers can't do for you, which is determine causation. Humans are uniquely good at determining and misdetermining causation, but computers suck at it. So you want these in time series. If I look at it, we'll zoom in on this right here. So this is the average across just 2 days, right? And the same thing, there's latencies on a system, we're trying to aim for 10 milliseconds. This is fully extended, right? So the average here goes up to 0.04, which is awesome. This service looks pretty good. This is the histogram of that same time frame. It looks similar to the other one. This one only has 1.6 million samples in it. It's over 2 days. This is what the time series histogram looks like. It's kind of interesting. There's all the bands. We can see we have a whole bunch of modes in there. But it also clearly kind of goes off the top. I have this fixed at 0.05 as the top of the y-axis. That's not good. Hold on a second. Good to remember that with the histogram views, instead of having an average, which is 1 point, one of those little vertical slices, which in this case is a minute, or 5 minutes, sorry, 5 minutes, has 80,000 samples in it. So you have 80,000 latencies that you're actually looking at. So now if I calculate something like a P95 over that, I see that's probably, it's okay, right? I think I violated over there. This is 0.01, so that's 10 milliseconds. These are seconds. So 0.01 is 10 milliseconds. That's not too bad. So the interesting part here is that when we look at percentiles and you calculate P95 and you get a time out of it, you can conceivably invert that function and say, well, maybe 95% isn't the right amount, but 10 milliseconds is a really good assessment. So what percentile is 10 milliseconds? All right, if you have the data, that's not a hard problem at all. You can just invert that function, and you can start seeing percentiles. So if you look on the right side of there, it goes down to about 95, and it goes up to 100. So the whole band there is 95% to 100%. Everything's in there. But this is that graph kind of turned backwards on a different parameter. So now I'm looking at, this is 10 milliseconds. But what percentage of the population is faster and slower? So on average, I would say it's between 97 and 98% through that graph. That's where the breaking point is. That kind of gives us a good hunch of how close we are to screwing ourselves with our SLO, right? So when you have 95th percentile and you know that 5% are slower than that, you don't know how much slower they are. They could all be 11 milliseconds and the world could be a wonderful place. They could also all be 700 milliseconds and every user is getting screwed. You just don't know. You don't know anything outside of that one tiny hairline, that 95th percentile. You don't know what the population looks like between 0 and 95, and you don't know what it looks like between 95 and 100. So by inverting that, you get another hairline that gives you a kind of a different idea around that. And if you have all of the data, you can arbitrarily start changing values and say, that graph is nice, but what if we were to do 50 milliseconds? Is 50 milliseconds fast enough? And it's amazing when you go back to someone and you're like, yeah, 50 milliseconds is totally fast enough. You're like, well, why the hell are we trying to aim at 10 milliseconds then? Right? So by being able to move these numbers around, you actually can look at the systems that you have and say, hey, you know, we actually have a really stable 99.5 percentile here at under 50 milliseconds. That's really stable, and I can see like distinct service problems in that. So this is easier to visualize. It looks better on paper. Now we can set a 99th percentile at 50 milliseconds, which is actually feels better than a 95th percentile at 10 milliseconds. Feels better, not mathematically. Feels better to marketing people. But by being able to tune those parameters around, it allows you all of the flexibility you need to be able to set reasonable, accessible service level objectives. So in this, there are three things. Time absolutely matters. So the quantum over which you use to assess your percentiles is really, really important. So I heard, I think yesterday, someone was talking to me about using a 7-day rolling window for their percentiles, which I actually personally think is a horrible idea. What it means is that every day, every 5 minutes or so, your window slides 5 minutes forward in time, but like there's nothing you can do to fix mistakes. For 7 days, you carry those mistakes forward in your calculations. Right? I don't understand why you would reevaluate and reincorporate a specific 5-minute window into 7 days worth of calculations. That doesn't make sense to me. I'm open to a different explanation of why that's useful, but it's really important to think about why you use the windows you use. And it also, because SLOs usually feed into SLAs as well, so it's really good to understand what your probability of hitting your SLA is. Right, so you want to construct SLOs that are achievable, because bad news when you miss them, because eventually somebody's going to put it in a contract and you're gonna get screwed. Uncertainty matters a lot too. This idea, where we check 99th percentile at 50 milliseconds, like both of those numbers are arbitrary. So it's critically important that you're able to change those parameters over time with history to kind of see like, maybe this SLO isn't right, maybe this one is a better one, it's more representative of what we want to deliver, it's easier to evaluate, and look at our history. We hit it when we were supposed to, and when people were unhappy, we missed it. So it's a really good surrogate value for our customers' experience. But you need to be able to tune the parameters to be able to do that. And histograms matter. So you either need to store all the samples, but when you start getting into systems monitoring, storing 1 billion samples a second is expensive. Storing a histogram of that data is not expensive. It's cheap. You just store bins and counts. So that's really the thing. So time, uncertainty, parameter tuning, and having histograms allows us to do this at really high scale. So I think that before I go on to tenets of monitoring, I think that SLOs are critically important. We've talked about them. Almost every session has mentioned SLOs or service level indicators, SLIs, or service level agreements, which we try not to talk to because they're legal. But they're all related to these same things of quantifying the type of service and the quality of service you want to share with your customers. And it's critically important that you be able to measure them accurately and that you can change the definitions of them over time and understand you're not going to get them right. Right? So you need to understand that you are not going to get them right and have the flexibility in your system to both change them and reflect on what that change would have meant in the past. So going over a postmortem and saying, would we have detected this error better if we had a 99.9th percentile SLO? And if the answer is yes, then maybe you incorporate that into your SLO check sheet. All right, so some tenets of monitoring, kind of switching subjects into pure just monitoring 101. The first rule of monitoring is that you don't ever measure rates. All right? I know how electricity works well enough here. I don't know if water's billed the same way. But you don't get billed by the rate. The electric company doesn't look at how fast you're pulling. They look at how much you're pulling. Right? You do a meter measurement at the end of the first of the month, and you do a meter measurement again at the end of the month. And if you want to know, on average, how much power you're using at any given time, it's rise over run, right? You just subtract the two numbers and divide it by the amount of time elapsed. That is a rate. But if you miss one of those measurements, so if you're tracking packets per second out of an interface, or octets per second, or connections per second, if you miss a connections per second measurement, you have no idea what happened then. If you measure a count of total packets or total octets, that's why switches do not tell you packets per second, they tell you packets. Like, I just sent 700 billion packets, and now a second later I have 700 billion and 12 packets. So you know that 12 packets elapsed. What that means is that if you miss a measurement, you don't know exactly how much you were sending during that time range, but you do know how much you totally sent during the expanded time range. You can always calculate rates from actual gauge values, but you can't go backwards. So anytime a system is showing you CPU utilization, for example, like you're 35% utilized, if behind the scenes they're actually sending 30% over, you are getting wrong answers. So you need to be tracking CPU ticks. That's how Linux does it, for example. It tracks the number of centiseconds spent in a state. And it just counts up and up and up and up. And if you want to know the rate over a specific amount of time, you measure in the beginning, you measure at the end, you subtract, and you divide by the time interval, and you get per second. Turns out that when you divide the number of elapsed centiseconds by the number of seconds, you get 100 times the rate, which is a percentage. It's kind of magical. Actually, it turns out to be like 98%. So you should always be monitoring quantities of things and not rates. The second thing is that you need to monitor outside the tech stack. And what I mean by this is not monitor from outside the tech stack. We'll get to that in a second. It's that if you're only looking at your computers, you're probably not servicing your business very well. I remember distinctly, and it's in for like the 4th chapter of my book, there's a little anecdote in there, being called at like 3:30 a.m. by a customer screaming at me that their systems weren't working. Their business was not working right. They weren't selling things. And I was like, man, we monitor everything here. I know the temperature on every CPU. I know everything. And he's like, I don't fucking care if my servers are on fire if they're selling things. And it was like, well, I guess that's true. I care. That's why I monitor those things. But the fact that he was able to look at data and assess that there was a problem, and I wasn't looking at that data, meant that I was stupid. I had absolute oversight. I should be looking at all of that data. If marketing is looking at data to see if that they're succeeding, there's no reason that shouldn't be in the monitoring tool. If business has KPIs around metrics and performance, there's no reason those shouldn't be in the tool. You can correlate systems failure with people missing their bonuses, right? This is real world stuff. So when a system crashes and it's completely burning, and the business is fine, but you have 0.5% of introduced packet loss in a switch, and things look okay, but the business is tanking, chances are if you didn't have that business-related information, you would prioritize the solving of those problems wrong. A system broken and on fire always seems more important than some sort of smidge in a percentage somewhere, but the outcomes can be completely different. So by monitoring outside of the technology stack, you can see that. Comes with do not silo data. So I know that everybody wants everything distributed, but if you don't have your data together, you can't do correlations of the data together. So eventually, and when I say eventually, I mean within a second, you want all of the data in your architecture that monitors your systems, your databases, your users, your finances, all of that stuff in a single spot so that you can start building whatever business questions and answers and solutions around that data in one spot, right? So if you're going to apply machine learning or AI, leaving a set of data out of that system is probably a horrible mistake. So you do want all of that data together, which is why I think there's been so much investment across the industry in building highly scalable time series databases now. All right. Value observation of real work over measurement of synthetic work. So if you're going to, for example, on a systems level, anybody's run SAR or IO-stat in a while, there's an average IO read latency there. It's a little number. Sadly, every OS decides that it has a better way to calculate it, so none of them are standardized. But generally speaking, it tells you, on average, I've been performing read operations against this spindle, or this SSD, or this NVMe card, and they have taken this many microseconds on average. Usually it's an exponentially weighted average, right? So it's just a decayed average. That represents no transaction ever. There is a strong probability that no individual transaction actually took that latency. It's an average. You have no idea about the distribution. The computer did all of the work to do the I/O operation. It knows how long it took. There's no reason you shouldn't be observing the actual workload instead of the synthetic measurement or the synthetic byproduct of it. And the worst case scenario there is when you go do a disk IOP to figure out how long it took. This is the way we used to monitor. We used to run a query against the database and measure how long it took, and if it was fast, everything was good. That was the one query that didn't have to happen in the system at all. There were already queries running. It was a synthetic query. So always value observation of real work over the other. That said, you should be synthesizing work to ensure function in systems. Right? So there are times where no one's using the service, right? Even the biggest sites in the world have APIs that get one hit every 12 minutes or 15 minutes on a specific API, some bespoke weird one, right? You don't want to learn for the first time that it's broken when the first user shows up. So there are reasons, specifically in low volume environments, where it is completely not only acceptable, it's really fundamental that you synthesize traffic against that to make sure that it is actually working. If you have incredibly high volume sites, it's often unnecessary to do that. So like disk I/O ops, syscall latencies and things like that, you don't need to do a syscall to see how slow it is. There's enough going on. All right, and percentiles are not histograms. Period. End of story. 95th percentile, it is not a histogram. If I give you a time series of, if I show you the 95th percentile over everything and I say, what do you think the 97th percentile is? The only answer is, I don't have a clue. It's the only answer. You do not have the data to answer that question. If you have minimum, which happens to be the 0th quantile, and maximum, which is the 100th percentile, go figure, you at least know where it's bounded, but still you have no idea what that distribution is. So anytime you're looking at something where you have percentiles, and they're incredibly useful statistical aggregates that come out of something, if you can't change the percentile there, then you really can't explore what that distribution looks like. You want to be able to count the modes and things like that. So you should be storing things. Histograms are the most efficient way to do that, but you can just store all the raw data as well to calculate that. Another thing is that history is critical. And I've seen a lot of monitoring places downplay this. There aren't too many commercial vendors that downplay this, but there are some open source ones that are just like, yeah, we only store data for a month in the system because anything older than a month isn't important. Wrong. That's just flat out horrible, right? You don't store it because the system wasn't designed to store it. That's valid, I'm fine with that, but it doesn't mean it's not important. So, and I'm not talking about a week or a month, I'm talking about years of data, and I'm talking about data that allows you to do postmortems. So when you look at data and you have minute-by-minute data or second-by-second data, you can actually ask questions later about that data and go back and find it out. So the idea of your history kind of rolling up into a 5-minute super-aggregate or an hour, I don't know if anybody's used RRD tool. Amazing technology, it made compromises. It's a bad idea today. It was great when it came out. But the idea is that like I have minute-by-minute or second-by-second data, and then after a week, it goes into hour-by-hour, and after 12 months, it goes into day-by-day. There is nothing more infuriating to have a new question that comes out in the postmortem tomorrow. You have a postmortem tomorrow, figure it out, and you're like, this is a fantastic question. Do you remember that outage that we had 6 months ago? We didn't ask that question then. Let's ask that question now. And you go look at your graphs, and it's one big fat average over a day, and you can't answer anything, right? So you absolutely have to have the same data that you have tomorrow for tomorrow's postmortem. You have to have that 6 months from now. You have to have that 12 months from now. And it's really important to understand capacity planning for capacity planning as well. So you need the data to do capacity planning over the long term, but you also need the granular data so it's a fantastic example of that is bandwidth utilization. So if you look at the history of bandwidth utilization and you've averaged it out over a day, turns out you don't serve the same bandwidth all day long. I guess everybody knows that. It's a little humpy. At 3 a.m., nobody shows up. At 4 p.m., everybody's online. Depends on your business. But if you average it out per day, your maximum is completely obscured. You have spike erosion, effectively. So all of the maximums are gone, and you're planning this trajectory curve that doesn't accommodate your peaks at all. So having that sort of granular data means that you can really answer all of the questions correctly. So history is critically important. And then outside of monitoring slightly is alerting. So the only reason we should be monitoring things is to know what they're doing. And if they're doing something wrong, probably someone should fix it. So that's where alerts come in. And one of the worst parts of alerts, I'm sure everybody has been in an alert tire fire, right? Where it's like, alerts go off and you're like, oh yeah, that one always goes off at 11 p.m., right? So there's a big thing about alert fatigue. All of those things are real. There is no product in the world that will save you from configuring your alerts crappy. Okay, that requires human discipline to say, I am only going to alert someone when they have something to do. And what I found in my experience, that there are some rules that you can attach to alerting that introduce burden that prevents people from writing shitty alerts. And these are those. So if you have to have a human readable explanation of the alert, you don't get a lot of spurious, like, I'm gonna set that to 85%. And a human readable explanation of an 85% disk space alert is not the disk space hit 85%, all right? It's an actual, like, why is this important, right? What is the business impact of this? Describing that. Listing out the stakeholders is included in that. So when this actually goes wrong, and I have to explain myself, which executive or team lead or project manager do I have to talk to about this? There should be a fully attached remediation procedure for this. The disk space is 85% full. If it's like, set it to 86% and wake up tomorrow, it's probably not the right alert. So you actually have to know what you're supposed to do about it. You shouldn't be alerting unless there's an actual action that someone should be taking. And those actions can be vague. Sometimes you should be creating a meeting for that, and ideally you've automated that through the calendaring system, so you didn't get alerted, the meeting was created instead. And then you should have escalation documentation for it. So that's critical for alerts. And I only have two more, but be outside the blast radius. This is one of the most common mistakes that I see in alerting architectures, is that people got all this fancy alerting and all this graphing and all this ability to observe their system's behavior, and their system breaks and the alerting is inside the damn system and they can't see anything until they get it back online again. So the actual outage that they are attempting to use monitoring to understand and remediate is inside the problem and they can't use it. So move your data away from the problem. So when the system fails or the system malfunctions, that the alerting, the monitoring, the alerting, the trending, all of the analytic systems around that data, the visualization paths, everything, the tools that operators need to understand the system, you're not, I mean, this goes back to chat ops as well. Like, what happens when the site is broken? Everybody tries to fix the site. It's the most important thing. They all jump on IRC or Slack or something. What happens if that's broken? The site is no longer the most important thing. IRC is, right? IRC becomes the most important thing in an outage because it's the only way to make progress on the other more important problems. The same is true for observability systems in general. They have to be more available than the systems they monitor. So it's important that they be more simple, and it's important that they be outside the blast radius. And with all of that said, for God's sake, something is better than nothing. So if you have nothing, feel free to just screw it up to get something there. I see a lot of times that people let perfect be the enemy of good, and there is no way you're going to have perfect monitoring. So it's really important to start. And I always really like to start at the top of monitoring. A lot of people are just like, oh, the first thing you need to do is instrument a system. It's like, okay, my systems don't have pet names. It's not like Freddy. I don't really care about my systems that much. I do care about my services, but actually what I care about is getting paid. So maybe some top-level business indicators would be really good. How about our stock ticker symbol? That'd be pretty good to monitor. It's pretty easy. If that crashes, I think everybody's got a lot to worry about, right? So then you go from there, you go to, if you're a user-facing website, traffic volume. Egress traffic is probably the most significant and highly correlated surrogate measurement of success. If your traffic is there, your business is doing okay. If it disappears, you got a whole lot of problems. So look for the highest value return things and just get them monitored. But then when you start going down, keep going. It's a rabbit hole, but it's worth exploring all the way to the bottom. And when I say all the way to the bottom, I mean the latency of every IOP, the latency of every syscall. I see that coming. It's like all monitoring. There are so many times where a customer will come and sign up for Circonus and turn something on, and it'll be the dumbest monitoring ever, like a ping time or something like that. But they just didn't have that facet. They didn't have that view. Could have gotten that view with any tool, but they just turned it on, and it asked one question. It was like, why is it higher from Nagano, Japan than everywhere else? And it's like, oh, because it's Japan, it's far away, right? And it's like, yeah, but it's 800 milliseconds higher. Okay, there's no place on Earth 800 milliseconds away from any other place, right? So why? That question is Eureka. Like, that's what monitoring is supposed to do. That's what observability is supposed to do. It shows you the behavior of the system. You already have a mental model for that system. It's going to question that. And if you can't explain what's on the page, the rewards for diving in are usually epic, right? It's like, hey, there's a latency of 1 second. Is that acceptable? Yeah, probably, but I can't explain why, and I don't think it should be that way. And suddenly you get some sort of 30% performance improvement. Like the low-hanging fruit that shows up by just seeing your system in a new way is unbelievable. So find the bottom of the rabbit hole. And that's it. Thank you very much.